In this video, we discuss single sideband EM signals, shorthanded SSBVM. Before we proceed further discussion, let's review the DSBSC EM signals and conventional EM signals. I'm going to show you the page 3 in our formula sheet. We have all the formulas been listed here. DSBSC signals here, double sideband suppressed carrier. So this is a modulated signal. You multiply the message directly by the carrier. And this is a frequency domain using the modulation property, right? And this is a bandwidth for this modulated signal. For the modulated signal to occupy, that's 2W, and W is the bandwidth for the message. And this is the transmitting power for the modulated signal. Conventional EM, this is a modulated signal. And pay attention that the message has been normalized. And this is a frequency domain here. We can see the carrier is transmitted here. In this case, there's no carrier transmitted, therefore the name suppressed carrier. The bandwidth for the conventional EM is also 2W, which means that the modulated signal needs to occupy double the message bandwidth. And next, we want to look at the single sideband because we want to reduce the bandwidth of the modulated signal such that we can transmit more users given the total bandwidth of the channel. To understand the single sideband AM signals, we need to review the double sideband suppressed carrier AM signal. So this is a DSBSC signal. U of t equals to AMT. That's the message multiplied by the carrier. Now let's look at the frequency domain. Suppose this is the shape of the message. Okay, the magnitude here is 1 here for simplicity. And then what is U of F? The spectrum of the modulated. So this spectrum move to FC and here, and 0 become FC, and this point become FC plus W, and this point become FC minus W. And the same thing for the negative portion here. And the magnitude here become half AC. And this notation, AC subscript C, this is a LaTeX notation. After compile in LaTeX, it will show AC divided by 2. AC come from here because the magnitude of the carrier is AC, and half come from the modulation property. And this portion is half AC M F minus FC. See, for the modulated signal here, and this portion is upper sideband, and this portion a lower sideband. And one thing we can observe here is that the lower sideband, this portion and this portion, are symmetric. If I know this portion, I know this portion already because they are symmetric. So therefore, that's the idea of the single sideband. We can only need transmit either the upper sideband or the lower sideband. And you can see DSBSC signals is not that bandwidth efficient because they transmit two sidebands, they are symmetric. So the idea of a single sideband AM signals is we're going to transmit either upper sideband, or lower sideband, not both. So to save the bandwidth. How do we do that? A simple way is to apply filter, a bandpass filter. So this bandpass filter starts with FC and cut off at FB, and FB is to be greater than FC plus W, a little bit greater, not smaller. You can make it equal, that's fine. On the negative part of the frequency For the bandpass filter, the spectrum is symmetric. So here is FC, here's minus FC, here is FB, and this is minus FB. I assume the magnitude of bandpass filter is 1, just for simplicity, because I don't want to attenuate or amplify the signal. So if I pass this DSBSC modulated signal through this bandpass filter, I assume output is U of B T. So what is the frequency domain? We know that frequency domain, that's the spectrum multiplied together. So when two spectrum multiplied together, we line up the frequency. So each frequency we line up, and then we multiply the magnitude, multiply the value of the spectrum. So bandpass filter, all this portion 0. So 0 multiplied by anything, that's 0. Right? It's this portion. And then starting from FC, this bandpass filter will pass the signals. Because of the magnitude is 1 here, I'm going to pass everything the same shape. This portion being passed through to here. Okay, and here that's FC plus W. The same thing on the negative portion of the frequency here. So anything in this portion is 0. 0 multiplied by anything, that's 0. And starting minus FC here, and this portion of spectrum being passed through here. Output of the bandpass filter here is the upper sideband. So if we transmit this signal, this modulated signal, this is a single sideband signal. Now I have a better drawing here. This is upper sideband, the positive portion. This is a negative portion.